Hello students, this is Anjana from Computer Science Department. In this class, we are going to continue the topic of number theory. Go for the next slide. Here in this class, we are starting with the topic called linear congruences. Here, linear congruences is about, it is an equation. It is in the form of Ax is equal to B modulo of M. Here we have already know about the modulus operation in this mathematics form. So here, how we are going to apply this congruence form in this information security? Why? Because actually, why we came up with the number theory is whenever you are providing network security, you have to provide some cryptographic forms. Why the what is the reason for the cryptography? Here, why the cryptography is came into the picture means. Uh, Based upon the cryptography itself, we have to provide the security for the any other systems. So to provide that security, we are coming for the number system concept. So in that number theory, we are having some mathematical forms and calculations, and based upon the modulus operations, based upon all these things, we are going to apply. We are going to apply all this number theory on the cryptography, so that we can perform the cryptography very effectively. Okay. So in this class, the linear congruences is about if the equation is in the form of Ax is equal to B mod M, we can say it is in the linear congruence. Here the congruence Ax is equal to B mod M has a solution if for X if and only if B is divisible by the greatest common divisor. We have already performed the GCD operations. We have already know about that. If you are going to perform the greatest common divisor operation, we need two integers, that a here the integer a and m, that should be in the form of Ax is equal to p plus km. Here k is a constant here. Go for the next slide. Here linear congruence is a problem. It does not having any solution. It may have only one solution, or sometimes it may have infinite or many solutions. These are the possible combinations that we are going to get with the linear congruence technique. First one is does not have any solution, or second one is it may have one solution, and the third one is it may have the infinitely or many number of solutions. So this is the example. If you have observed this example, this is examining the equation Ax is equal to 2 mod 6 with different values. 3x is equal to 2 mod 6. See here, the greatest common divisor of 3 comma 6 is 3. Definitely it will be 3. But since 3 does not divide 2, so there is no solution. So 3 2s are 6. So the quotient that will give it that will get is 2. So again, if you are going to divide 2, the in 3 table we won't get 2 there. So 3 does not divide 2. So there is no solution for that. Next one, 5x is equal to 2 mod 6. Here you have to perform the modulus operation for 5 and 6. 5 ones are 5. The remainder that we'll get is 1. The quotient we also will get is 1, which may divides any b. So there just be one solution, that is up to 0 to 5. So x is equal to 4. So here we are having some set of values 0, 1, 2, 3, 4 and 5, and are the set of at least positive residues. So we have to perform the modulus operation there. Here exactly if you are going to perform the modulus operation here, 4x is equal to 2 mod 6. Here d is equal to GCD of 4 comma 6. That is, if you are going to perform the modulus operation there, then 4 ones are 4. The remainder that will get is 2, which does divides 2, and also there is exactly two solutions, that is 0, 1, 2, 3, 4, 5. Here x is equal to 2 and the answer is x is equal to 5. So here by this what we are getting is, if from the linear congruence technique, sometimes we does not having any solution. Sometimes we may get only solution. Sometimes we may get many solutions or the multiple solutions. This was the problem with the linear congruence technique here. Suppose if this is the example. This is the example. Here the equation should be in the form of Ax is equal to B mod C. Here 3x is equal to 2 mod 6. That is, we are going to perform the modulus operation between 3 and 6. Here the 2 is the quotient that we are going to get here. 3 2s are 6. 2 is the quotient here. So 2 does not here the 2 does not divisible by anything, so it does not having any solution. But here 5x is equal to 2 mod 6. Here d is equal to GCD of 5 comma 6, that is equal to 1, which divides by any b. So there is just one solution, that is 0 1 2 3 4 5. Here x is equal to 4. Suppose we are having set of at least positive residues. We are having some po possible problems just like that. There are only exactly two solutions, that is we are having up to 0 1 2 3 4 5 and x is equal to 2, and we are having the answer x is equal to 5. See, this is a possible case of infinitely many solutions. For example, 3x is equal to 4 mod 5. That is, we have to perform the modulus operation between 3 and 5. That is, first time we'll get 0 and 0 for 1 and 3, 2 and 1, 3 and 4, 4, 2, 5, 0, 6, 3, 8, 4, 9, up to just up to that. We are having possible combinations of the solutions. This is also another case. If it is true, then in this case, if we are having the value of x is equal to 3 and value of x is equal to 8, if it is also true when the value of x is 13, 18, 23, just like that. In general, if r is an integer such that ar is equal to b mod m, then all the integers are like, r plus m, 2m, r minus m, r minus 2m, just like that. These are the possible combinations of if we are getting infinitely many solutions in the congruence technique. Okay. See, then how we are going to solve this linear congruence problem. See, a linear congruence is, suppose if we are having ax is equal to b mod m as a solution, if and only if a comma n modulus of b. You can solve the linear congruence by finding the modular inverses by turning the congruence into the linear Diophantine equation. That is, suppose if it is in the linear congruence form, if you are going to find out the modulus operation and inverses by turning it into the congruence, then it will be a this particular type of equation. Suppose, and if it has a solution if and only if we are having a comma m modulus of b, then we can easily solve that equation. Suppose if we are going to solve the linear congruence by finding the modular inverse by tuning the congruence into the linear Diophantine equation. Next, this is what is the primality test. Here, the primality test provides the probability whether it does not having the large number. Suppose, see, if we are going for a prime number, so many types of prime numbers are having, we are having here. But when it comes to a large number of values, we are having so many lot of it's not a definite set, it is an infinite set of infinite set of prime numbers we are having. But in a primality test, the probability here, where we are going for the probability whether in the primal test we are going for a probability whether there is a large number is a prime or not here, and the several theorems including here, how many number of theorems here we are including is we are including the so many several number of theorems here. But in order to provide an idea, but we have to go for the test called primality test. Then based upon this test, we can't get an idea about that how we are going to give the probability for that particular number of large numbers. Then then definitely we should go for the then definitely what we are going to do is we should go for the cryptographic scheme such as RSA algorithm. It is heavily based upon the primality test. See, if you are going to do a primality test, then probability is not a essential thing that we are going to apply, but this is a major thing that we have to follow. And also the several, what are the, not only one theorem, several theorems what that are including in the Fermat's theorem, it will provide an idea of primality test. But cryptographic schemes such as RSA algorithm, it is heavily based upon the primality test. Here this test we have already said it already provides the probability whether we not having the large number. Okay, then go for how we are going to implement that. These are the definitions. So a prime number is an integer that has no integer factors